Okay, good afternoon everyone and welcome to the talk. So the title says that says WebKit's just-in-time compilation, but most of what we discuss is going to be applicable for all other browsers as well. So thanks Rana for the introduction. We can get straight away to the content. Just a second, let me adjust my slides here. Yeah. So JavaScript. I think most of you are familiar with JavaScript. JavaScript is an untyped and an interpreted language. So if we have a statement that looks like let x is equal to a plus b, what happens is that it is first converted into bytecode. Bytecode is a form of representation of code that is a bit lower level than the original source code. And the bytecode is actually executed by the JavaScript virtual machine, which is the interpreter. Now JavaScriptCore, which is JSC short for JavaScriptCore, and JavaScriptCore is WebKit's JavaScript engine. The bytecode for JavaScriptCore looks something like this. So you can see that each bytecode consists of an opcode followed by a few operands. So it's kind of like assembly, but it's a bit higher level. So now let's talk about the interpreter first. The interpreter is the code that actually executes the JavaScript bytecode. To visualize this, you can just think of the interpreter as a huge switch case that switches on the opcode, and each case is a handler for that bytecode op. Let's just see that in action. So typically JavaScript code is first converted into bytecode. Bytecode is represented as an array. For example, the first one is add. First one was add. And the interpreter, what it will do is that it will fetch one instruction from the bytecode. It will resolve the handler for this instruction and execute it. And after that, it will update the PC to point to the next instruction in the bytecode. And this loop is going to go on. So this is basically a fetch, resolve, update. First fetch the bytecode, resolve the handler, update the PC. However, this has a few problems. One of the main problems is that the fetch, resolve, update cycle that this is following is actually pretty slow performance-wise, especially when we are talking about repeated code execution. For example, like your JavaScript code has a for loop. So each instruction is going to be fetched, resolved, and updated like thousands of times. So this makes a lot of performance loss. Another issue is that JavaScript does not have types, so the interpreter needs to, so if we have a statement like this, A and B can be any type. So the interpreter has to provide for all possible types of the statement. Another issue is that bytecode does not have any dependency between opcodes. For example, if take this JavaScript code, we are actually, if you assume that A and B are integers, we are actually computing A plus B 3 times, whereas we could have ideally done something like that, add A plus B and store it 3 times. But instead we are going to compute it 3 times. So this again leaving performance on the table. The solution for this is to compile the bytecode into native assembly. But this is only viable if that bytecode is going to run multiple times. For example, if there's a for loop in the JavaScript function. So then it's viable to compile JavaScript into assembly. So in order to solve the various problems that are faced by the interpreter, we have multiple JIT compilers implemented in browsers. One of the first compiler is the baseline compiler, which solves the repeated cycle issue. Let's see that in action. So let's take this very simple JavaScript code, addition, multiplication, object creation. This is first converted into bytecode, and what the baseline compiler is going to do is that it is going to take one instruction of the bytecode and convert that to assembly. So here, just load the arguments into the registers and call the handler function. It does the same for the store, and it does the same for the rest of the instructions. So this is just sudo x86 assembly. Now the interesting point is that in the baseline compiled code, there is no fetch. In fact, there is no reference to the bytecode array at all. It's all assembly. There is no update, there is no handler resolution. So the entire fetch resolve cycle is gone now. We just have assembly code, raw assembly code. So this provides considerable speed up over the interpreter. However, The baseline compiler makes very little optimizations, very few optimizations. We are going to see a couple of them. So the resultant code is not the most efficient. You don't have to read this, but this is how the JavaScript code's baseline jitted code looks like. You have the add instruction and followed by the assembly for that. One point to note here is that you don't see that call instructions that we actually saw there. Call handles some, you don't see that call instruction anywhere here. That is because baseline is a bit smarter, and when I was compiling this, I used both the operands for this add as integers. So the baseline, what it did is that it actually emitted an add instruction directly instead of having a call, and followed by a store. However, it also has checks. If either of the operands are not integers, it goes to something called a slow path, and in the slow path we have that call to the resolution function, the interpreter. This is the generic call. Now this fast path, slow path thing is one of the optimizations that is done by the baseline compiler. Basically, optimize the common case. That's what it's doing. Another thing it does is inline caches, but before that we need to look at how objects are represented in JavaScript. Consider this object X, which has two properties and two elements. In memory, this is actually represented as a pointer, as a combination of 3 pointers, the shape, properties, and elements. Just keep in mind that I'm just talking generically here, so each engine might tweak this a bit. For example, Chrome might have a slightly different notation, but in essence it remains the same. The shape is something that contains the property names. You can see prop1, prop2, but it does not contain the property values. The property values are contained in the properties pointer, and the elements are contained, 1, 2 are contained in the elements pointer. You can see that in the shape we have a few offset, and you might have guessed what it is already. Prop1 is mapped to 0. That means that if I want the value that is associated with prop1, all I have to do is look at the 0th index in the properties array, and same for the 1. So how do I actually for example, there you can see we are accessing a.prop2. What does the engine do, JavaScript engine do? It first fetches the shape, then it iterates through all the properties in the shape. It sees prop2 there, fetches the index, goes to the properties array, and goes to the required index, which is 1, and fetches and gets 1337. It's the value of prop2. However, this is a bit slow and can be optimized. In order to optimize this, JavaScript has something called inline caching, and it attaches a cache to that property there, property access there. This is a cache with 3 slots. So what happens now is that the shape is accessed, it checks the cache, but the cache is empty. So that it goes by the default way, the one we just discussed. However, after the default way finishes, it updates the cache. The cache is updated with the shape as well as the property offset of prop2, which is 1. So the next time we see a shape S1, it will check the shape in the cache with the shape of the object. If that shape matches, we have a cache hit. So now we don't have to access the shape on top at all. We can straight away go to the properties and access the first index. However, there is a different shape. If there is a different shape, then it's a cache miss, because S2 does not match what is there in the inline cache. So there is a cache miss. And if there's a cache miss, we go the default interpreter route and fill the slot with the new index. So basically this cache keeps track of all the structures that are seen at this point along with the property offset number. So from the problems that we discussed with the interpreter, the first one is solved by the baseline JIT. The second one is also kind of solved with baseline JIT's fast path slow path approach as well as the inline caching approach. However, the third part is never solved. There is still no, the baseline JIT still has no dependence between objects. For this we have something called optimizing compilers. Optimizing compilers are slow to generate code. Optimizing compilers do not work with the bytecode because bytecode is not optimal here. So optimizing compilers always have their own representation of code. However, the code that optimizing compilers emit is very much more, much more faster than any of the other ones. More the optimizations, more efficient is the code, but slower is the compilation. So typically to offset for the slow compilation, what browsers do is that they have multiple compilers, not a single compiler, multiple compilers, each compiler doing more optimizations than the previous one. Also, for compiling code, you need types, and JavaScript is an untyped language. So all the optimizing compilers are going to speculate on types, just like the baseline compiler did. So pictorially, the previous slide it looks like this. Source code is now parsed by the parser into bytecode. Bytecode is consumed by the interpreter. The interpreter executes the bytecode, and the baseline also executes the bytecode there. And the profiled bytecode is now passed to the JET compiler, which emits an optimized code. And if there is a speculation failure, it goes back to the interpreter or the baseline compiler. Now let's shift gears to focus more on JavaScript core and less on the other browsers. JavaScript core has 4 tiers of execution. We already saw the LLint, which is the interpreter. Then we also saw the baseline JIT. However, the other two, DFG and FTL, are optimizing compilers. So FTL is the fastest, emits the fastest code, but it also takes the longest to compile. If there is a speculation failure in DFG or FTL, control flow shifts back into baseline. So you can think that you can see all this complexity there, and more the complexity, more the chances of bugs. I was saying that interpreter always works with bytecode. We also saw that baseline also works with bytecode. However, DFG works with a different representation of code called DFG IR, and the FTL works with 3 IRs. It works with the DFG IR, of course, but it also has 2 unique IRs of its own, called B3 and AIR. Now, let's talk about typing in DFG. In DFG, types of JavaScript has variables, and types of variables in DFG is represented using 2 things, speculated type and abstract value. Now, both of them represent the type of a variable in JavaScript. Now, speculated type actually signifies the most possible value of the type. For example, if I have a JavaScript variable that has the speculated type int, it basically means that most probably this variable is going to be an int, but it can also be anything else. However, if an abstract value says that the JavaScript variable has type int, it is going to be int. It can be nothing else. This means that speculated type needs to be checked at runtime because for all purposes, it's just a guess. Educated guess, but just a guess. So it has to be checked at runtime. The abstract value is a compile time compiler proves it at the compile time, so it never needs to be verified. It is trusted by the compiler. Speculated type is calculated using profiling data, whereas abstract types are calculated using something called DFG AI. AI stands for abstract interpreter, not artificial intelligence. And speculated type is used to construct RIR, whereas abstract value is used to optimize RIR. They have their own functions, and they don't conflict with each other. Now let's look at how abstract values are actually represented in memory. So if you look at the source code for JavaScript core, everything is in C++. This is the structure that actually has the abstract value, that actually defines that abstract value. So it has a field called M structure, which has a list of all possible shapes an object can have. In JavaScript core, that shape thing that we saw earlier is also called a structure. We are going to use that interchangeably. Structure means shape, shape means structure. So this M structure is a list of all possible structures a variable can have, and M type is a list of all possible types this variable can have. Kind of conflicting, right? So let's do this with an example. Let's say a variable has M structure as, let's say, S1, structure S1, and a type int. What this means is that this variable can either be an integer or an object with type S1. It can be nothing else, integer or an object with type S1. We are going to skip the next 2 next to objects for the purpose of this presentation. Finally, we have the m value field. What it signifies is that it holds the address of an object if an object is constant. Let's do that with an example. Take this JavaScript statement, for example. This has the const specifier added to it. What this means, what this const tells is that this object can never be modified. So if you try to do object equal to 5 later, that's a JavaScript error. So that means the abstract value of this object will have the m value field as the address of this object because it's never going to change. So the m value is the address of the object. It's important to note that m value and structure do not conflict with each other, mainly because I can modify the value of the object, however the structure, so that the structure changes, however the address of object is still constant. So m value and m structure do not conflict with each other. There are two special values that each of those fields can hold. One is called the top, which stands for anything, and one is called the bottom, which stands for nothing, a null set. So this means that if m structure is top, this means that this variable can be any type, any type. It's an object, but it can have any type. However, if the m structure is bottom, then it basically signifies that this variable it will have no shape at all. That means it's a primitive value, integer, float, or whatever. The abstract interpreter is used to find the concrete type of the node. It also has other implications. For example, it's used for constant folding, but constant propagation, but we are not going to discuss that here. Remember that if you are reading the source code, it's always called DFG AI or AI in the source code. AI stands for abstract interpretation. Now we're going to look at a bug in the abstract interpreter itself, but to do that, we have to be more familiar with property accesses in DFG. You're probably familiar with this now. We are accessing a property P1 on an object. Whenever interpreter sees something like this, it attaches an inline cache, IC, and the IC right now is populated with S1, 0, shape S1, offset 0. So when DFG tries to optimize this, it splits it into two opcodes. One is the check structure and one is the get by offset. The check structure checks the structure of the object, this object, with S1. Where did it get S1 from? It read it from the cache. And the get by offset fetches the actual property from offset 0. Where did it get the 0 from the cache? So DFG basically bakes the inline cache into the IR. An interesting point to note about check structure is that if that comparison fails, this is basically a comparison. Check if object structure is same as S1. If that comparison fails, this is a speculation failure and no further code is executed. So now let's look at an example. Just take a moment to read this JavaScript code. It's just creating three objects, x1, x2, x3. x1 has the shape S1, where P1 is at offset 0. This one has shape S2, P1 is at offset 0 again, even though shape is different, offset is same. This one is x3, shape again is different, but offset is again in this case the offset is also different. P1 has the offset 1, the other two had an offset of 0. And a point to note is that we are going to be studying the property access arg.p1. Now we know that arg.p1 is going to have an inline cache. The data in that inline cache is represented in JavaScriptCore using a class called getByStatus. So this is again a class, and this is used to track the property access. GetByStatus is used to track the property access of that issue, of that property access. And now we can forget about all the other fields. The only field that we care about is this vector. This is a vector of getByVariant. So now we have to go into getByVariant and we have to disassemble it. It's a complicated structure. You do not have to read any of that. What you have to note is that the getByVariant is something that keeps track of structures with similar property offsets. Again, we'll see this with an example rather than this thing. So let's bring that example which we saw earlier. X1 and X2 have a shape S1 and S2, and the point to note is that both have P1 at offset 0 even though their shape is different. So this means that V1 is a variant, so get by ID variant with that holds S1 and S2, and V2 is a variant that holds S3. The point here is that if your offset is same, you have a single variant. If your offset differs, you have a new variant. So S1 and S2 have the same offset 0. So they are both clubbed together in a single variant. Whereas S3 has a different variant, so it has S3 has a different offset, so it has a different variant. The get by status is a vector of all these variants. Now, what we are going to do is we are trying to ask how do we create this get by status to create all these variants, statuses and all. What we need is that at this point arg.p1 we need to know what is the structures that arg can have. What are the structures that arg can have? One way to find that out is the inline cache. The inline cache associated with that arg.p1 access will hold all the structures that it has ever seen. But another way that we can compute that is using what we just discussed, are abstract values, because abstract values also signifies more or less the same thing. Speaking of abstract values, let's actually look at some buggy C++ code. So this is the code for abstract interpretation of get by ID. What is get by ID? Let's say we have an object.p1 access. Then if we have an object.p1 access, then the get by ID is an opcode that is the DFG opcode that signifies that property access. So first we fetch the abstract value of object, then we fetch the P1 as a string. It's string implementation P1, we fetch that. We compute the get by status that we just discussed using the abstract value. We already discussed that one get by status has multiple variants, and each variant now has to be, the for loop has to traverse over each of the variants. Now this is a complicated bug. I'm trying to simplify it as much as possible, but still it's a complicated bug. So now each variant as it is traversing, it's calling this inferred value for property. What this whole code is trying to do is to predict the abstract value of the result. Object.p1, we know the abstract value of object. What is the abstract value of object.p1? This whole code is essentially trying to find that out. So that is found by this property inferred value for property. Now what this function does is that it checks if object is a constant, const specifier for example, and if it is a constant, then it goes directly and fetches the offset that it's passed and fetches that value. So it knows the type of object.p1, and it does that for all the variants, and the results are merged together. However, this has a problem here. We are actually in the previous couple of slides, we are actually making an array access on the property offset in this code. But the offset is keeping on changing in the for loop. Initially it will be 0, then it will be 1. Offset comes from the for loop. And that should not happen because we are trying to access object.p1, which p1 is at offset 0. But this code is trying to access offset at 1. So this will essentially lead to an out of bounds error. It will lead to all kinds of error. Long story short, the code makes no sense here. No sense. So this is actually going to give incorrect results of the resulting abstract value. Because we can see that with an example again. Let's say we have an object. Let's say we have an object obj1, with two properties, S1, two properties, P1 and P2. Then both of the properties here are actually just pointing to the same value, and we have an access object here, property access. We are trying to exploit all property accesses. So let's say that somehow, we don't know how, but somehow the property access has the abstract value that's shown here. Two structures, S1, S2, and a value and a const value of obj1. So this value is effectively obj1, and the offsets are going to be 0 and 1. So what is going to happen here is that first we try to get the property at offset 0, which is, this is going to be P1, it's fine, it's correct. It's correct. In the next iteration of the for loop, this is going to be 1. This is an hour. This might or might not. In this case, at offset 1, we have P2. And we are trying to compile an access to P1, but the compiler is reading a property P2. The compiler itself is confused at this point. So it reads some incorrect value. The resulting abstract value is also incorrect now. So just to take a moment, abstract value is something that is trusted by the compiler, but due to a bug, abstract value is now wrong. So a trusted internal value is now wrongly computed. This means that we have avenues for type confusions everywhere here, from here. So one of the main places to look for type where abstract values are used is constant folding, because it's the constant folding case. So what is constant folding? Constant folding is basically an optimization phase in the DFG IR. And let's see what it does for the check structure output. To recap, when we have a property access like this, DFG converts it into two accesses. One is a check structure, one is a get by offset. Get by offset is basically fetching the property value, whereas the structure check is done by the check structure. And what this code is going to do here is that it first fetches the abstract value of object. What does the abstract value of object contain? It contains all possible structures object can have. And then it fetches S1 from here. This set is basically S1. Now, if the compiler asks the abstract value, what are the set of structures that this can have? What are the set of structures that object can have? And if the abstract value reports to the compiler that object can only have one structure, S1, then this entire check structure can actually be eliminated here. And now coming back to our code, our bug was that we have an incorrect abstract value for this, and if we access a property on that value, then check structure. This is a property access is actually split into two DFG opcodes. The check structure is incorrectly eliminated because the abstract value is incorrect. The check structure is incorrectly eliminated because check structure elimination is based on the abstract value, which is now incorrect. So we have an incorrect elimination. So we just have a get by offset, which is a direct pointer access without any checks. In reality, what happens is that the compiler thinks access object can only have the structure S1. However, in reality, it can also have the structure S2. So, which means that if it has the structure S2, which I didn't even show S2 here, it's just some random structure S2, then object.p1 can be a random access, can be a random number. It can be 1, 2, 3, 4. For all I know, access can be 1, 2, 3, 4. And this one is now trying to do a pointer dereference on 1, 2, 3, 4, which is wild. So if I run that in GDB, this is how it looks like. I crash with RCX as 1, 2, 3, 4 because this crashed the entire engine by doing an arbitrary pointer dereference. So from here, writing an exploit is actually simple from here. So we are not going to talk about writing an exploit, but it's pretty simple. And this bug was patched in, I think, November last year. It was introduced in 2014. This is a bug. this is a bug so complex that it lived in the compiler for 8 years. So 8 years Safari was vulnerable to, Safari could have been exploited using this bug. Only in November it was patched. So that's the advantages of complex bugs. Now let's look at a simpler bug, much more simpler bug. For this, we need to know what is a JS value. We know that if object is equal to, if we have JavaScript statement like this, internally JavaScript core actually stores obj as a pointer. Pointer means all upper 15 bits are null. Because that's how virtual memory works. The virtual memory only uses the lower 48 bits. So upper 16 bits are actually null. If we are storing a number, JavaScript core actually uses the pointer, uses this FFFE. So upper 15 bits are set. And finally, if we have a float is encoded using the IEEE 754 format. This is the 1.1, IEEE 754 will give us some value. And JavaScript core, what it will do in turn is that it will add 2 to the power 49 to our IEEE encoded thing. Now, if you have done bug hunting before, every addition is suspect to integer overflows. This means that if the upper bits of an IEEE 754 are all set, then this can overflow. So the compiler has to protect against it. In theory, it can overflow. In practice, it will never overflow. This is because the IEEE 754 format says that if the upper bits are all set, it's not a number. This is not a number. JavaScript only honors one not a number value, and that is this one. Everything else it does not honor. So now let's go back into the code base. This is the code that converts JavaScript IR, the DFG IR into assembly. So this is the code that's been compiled. We have an array access, and that array access is being compiled to assembly. However, this is not a simple array access, it's a floating point array access. Speciality of float 64 arrays here is that float 64 arrays hold raw floats, IEEE floats, not JS value. And another interesting point is that they are completely user controlled. We control every single bit. So this means that when we do a get by val, this means that when we compile it, the compiler should check. The compiler should actually check. First, convert the float into a JS value, and also check each of the bits. The compiler does check, convert the float into a JS value, but it never checks whether the top bits are set or not. So this means that we have an overflow here, which should never have happened, and we again have an arbitrary pointer dereference. Yeah, me and my colleague did a full talk on this, as you can watch this there. To conclude, some takeaways here are to hunt for assumptions in code and to compare implementations between various compilers. Another idea is to look for variants. This is that nan value patch that was patched. It was patched 2 times, 3 times, 4 times, 5 times. This bug has been there in the compiler since 2022. Every time in different parts. It's interesting to look at all the variants, and it's also interesting to look at the depth. The abstract value is so deep that it's lived in the compiler for 8 years. So finally, as a demo, this is the nan exploit running on an iPhone, and this is iOS 15, and it's actually reading the /etc/password. So that's more or less it. I'm told that time's up. Sorry for overrunning it by a few minutes. And I'll be around if anyone has doubts or questions. Then I'll be around the place.
Thank you, Vignesh. We can open the floor for a couple of questions very quickly. If anyone's got any questions, we can raise them now.
Yeah.
With such a complex code base like JavaScriptCore, how do you find the ability to like track virtual methods, bin call, and vtables like deep into the code base? Do you usually use that like dump disassembly or dump bytecode thing?
Yeah. So typically what people do is that you read the source code, but rather than reading the source code, I feel like reading the IR and the dumped assembly is more helpful than going and reading the source code. So I would say, yeah, read the IR and then read the source code.
Thank you so much for your talk. I was just curious how do you think how these two bugs were found? Like, was it through like auditing or fuzzing or thanks.
So the first bug was not mine. The abstract value bug is just a bug that I thought was so very interesting. The second bug is mine. It was found by me and my colleague. So it was found partially by fuzzing, partially by auditing, because we were auditing a code where a fuzzer actually found a crash. The fuzzer crash was not exploitable, but when we audited that code, we found a different bug. So we found this by looking at just reading code and yeah, mainly by source code auditing.
Any more questions? All right. For any other questions, you can take it on stage with Vignesh. Thank you very much, Vignesh.
Thank you.